is.
Now it's good. Okay, awesome. Are we good to go to start?
We are good to go and we are on time. So
Woohoo.
woohoo.
Awesome. Thank you. So I'm happy to be here today to present what we've been working on within the advanced cooling solutions in the immersion focus group there. We have developed a white paper. It's just about to wrap up and we're hoping to present it to the incubation committee here in next month. And the title of the white paper is Design Guidelines for Immersion Cooled IT Equipment. And the authors of this white paper is myself, Jessica Goldbrand from Intel. It's Jamil from 3M, Leonard from 2CRSI, Nigel from Vertiv, Rick from Flex, and Rolf from Asperitas. We have also reviewers of this paper, Alex and Larry from Green Revolution Cooling, Herb from Liquid Cool Solutions, and Rob from Dell. Also have acknowledgement of saying a big thanks to Henry, Mo, and Kai for the help on the electronics chapter. I will get to that a little bit later here. So the aim really of this white paper is to really address or discuss the design considerations that are different when it comes to immersion cooling. The community is generally very familiar with air cooling, but of course in immersion, if you're taking a system and you're putting it into a liquid, there are some other design considerations that you need to be aware of. And specifically the ones that we're talking about and addressing in this white paper is the following 5 here that is on the agenda. It's material compatibility, it's thermal design, it's mechanical design, software, and electrical considerations. So if we jump into it here directly, so I'll just give a very high level overview of these 5 different topics, to everything. It's not necessarily that in the material compatibility is something that we don't have to consider with other cooling technologies. It's just that complexity has slightly increased, right? If you're taking a full system and putting it into a liquid. So you need to make sure that there is material compatibility between the immersion fluid that is being used and all the components that are on the board. And therefore, it's also very important that you understand and know what wetted materials that you're actually putting into that liquid. It's also, you need also to understand the mechanism between immersion liquids and component interaction to determine mitigation options. If you don't know of what potential things that could happen when you're putting it into the liquid, you don't really know what to mitigate. One of those examples is really of, for example, looking at labels. Let's say that the glue that is used for the labels are not compatible with the immersion liquids and the labels will start floating around. There might be other ways of dealing with this, right? There are mitigation options. You might take the labels off. You might mark it with a pen that you know it's going to work in the liquid, or things along those lines. So there are mitigation options as well. And of course, the liquid itself, you need to be able to monitor the quality of the liquid over time, because you don't want, if there will be, for example, contaminants in the liquid, you don't want the performance of the liquid to degrade over time. So making sure that you're tracking it over time is something that is very important in immersion. And there are some methodologies for testing. So we're also discussing those in this white paper. And in the immersion world, we are dividing the liquids into hydrocarbon fluids and fluorochemicals, which are the ones that we're using. So hydrocarbons like oils, you need to do a general compatibility there. It's you can do put samples, materials or components into a liquid and potentially stress it, right? Thermally stress or potential other ways of stressing the compatibility testing that you're doing. When you're dealing with fluorochemicals, specifically for single phase, these fluids are very inert, but they might be materials that are leaching out to the liquid instead and being deposited somewhere else. They might interact with some other materials that you have somewhere else on your system. So this is what's called a secondary incompatibility, and that's something that you need to look out for when it comes to fluorochemical single-phase immersion. If you're dealing with the fluorochemicals and two-phase immersion, then you can use Soxhlet extraction, where you're boiling off liquid and condensing it and having that exposed to the material under test. And this is really in order to see if there are anything from the material under test that is either chemically reacting or leaching out into the liquid itself. And then you're analyzing that in the end. If we're jumping over, so again, quick overview of that. If you're looking at thermal design, there's a few different design considerations here as well when it comes to immersion. You can have, for single phase, you can either have forced or natural convection. So forced convection, you have a pump and you're forcing the flow through your IT equipment. Or you can use natural convection, where you're making sure that really natural convection is hot liquid is rising to the top and cold liquid is sinking to the bottom of the tank, if we're talking about the tank installation here. And the two, of course, if you have forced convection, you will always have as well forced and natural convection working together. So you want to make sure that they're enhancing each other. You could potentially enhance the cooling by introducing turbulence or unsteady flow. It might be unlikely or hard to introduce turbulence just due to the high viscosity that really is of these liquids. But you want to maximize the flow through the heatsink to make sure that you're getting that increased cooling capability. And again, cold liquid, you want to make sure in the same way as for air cooling, cold liquid to the hot components in order to get the most efficient cooling there. For two-phase immersion, you have boiling, so you're going from liquid to gas phase, and that's how really heat is transferred away from the hot components. And then in the top of the tank, it's you use condensation of having gas to liquid again, and the liquid is then dripping back into the tank. And here, you're not using a heat sink. You're using, if we would call it a simplified heat sink design, it uses a boiling surface instead to create nucleation sites to enhance the cooling capability. And here it's really of importance instead of being able to re-wet the boiling surface to make sure as that gas bubble leaves the boiling surface, that new fluid is coming in to make sure that you have efficient and continuous cooling of the hot components. What is different here compared to air is that low power components may not require heat sinks. You might be able to remove those. So here's an example as well. So I should say also, a lot of users today in single phase use air heat sinks in order for the cooling, really. Not necessarily, right, that the air heat sinks are not optimized for immersion. So there is still some enhanced performance that can be achieved if you're looking at designing an immersion heatsink and optimized heatsink directly for immersion. And some of the design parameters here to consider is really the base thickness of that heatsink, the fin pitch, and the fin dimensions of, as you see here, is an example of an immersion heatsink, that it has wider spacing and thicker fins compared to an air heatsink design. And as mentioned previously, component placement in the tank is of importance as well. There are, in the same way as for air, there are thermal shadowing effects in single phase immersion. if there is really thermal stratification of the immersion fluid in the tank, that you have cold liquid in the bottom and hot or hotter liquid on top, you want to make sure that you're placing those components with the most stringent thermal requirements at the bottom. And then for two-phase immersion, which is shown on the right side of this slide, it's really of generating that simplified heatsink design, which is a boiling enhancement coating, a BEC, onto basically a metal surface. And the parameters that you can vary here is coating thickness and particle size to vary as a function of depending upon what fluid that you're using. Here, the component placement in the tank, you're dealing with the constant temperature in the bath. You're operating at the boiling temperature. So it will be constant temperature in the tank, and there won't really be any thermal shadowing effects to speak of here. So it's a different boundary condition and environment compared to air. For mechanical design, the chassis design, there are some additional considerations that you need to take here as well. The dimension depends on tank size and the type of immersion. So here, there really are no standard tank dimensions currently on the market. Of course, there are some standard widths of 19-inch or 21-inch, but there's not really a standard depth of the tank. The chassis also needs to allow for high density solutions and fluid circulation to make sure that you get that flow of liquid through your IT equipment. You also need to address ergonomic considerations for installation and extraction, provide handles or reinforcement attachment points for lift to be able to lift it out of the tank. And having guiding features for installation and extraction is preferred to make sure that you're not banging in the IT equipment into something, another IT equipment box as you're extracting or installing. For software, we're not, there's again, differences here. We don't need any fans on the system in immersion. So removing those fans and having the IT equipment really, or the system management detecting that the fans are no longer there, but it still can operate because cooling is still being provided. That's something that needs to be addressed in for immersion systems. There's also some opportunities of being able to track fluid quantities or parameters of importance when it comes to immersion bath itself. For example, the liquid temperatures, the flow rates, liquid quality over time. Some electrical considerations. Component placement can be optimized to reduce loss or improve latency. And just highlighting here again that any immersion IT equipment should include detailed and robust test plan to ensure that any effects of immersion are validated. And this is, we're specifically pointing to signal integrity here and loss measurements. I will, of course, refer to the white paper here to get into any more details and talking about test methodology for this. So in summary, the design considerations for immersion cooled IT equipment, the different chapters of this white paper are material compatibility, thermal design, mechanical design, software, and electrical considerations. And this white paper is being wrapped up and expected to be presented to the incubation committee next month in December, we hope. And then we're hope to get back to you with hopefully that it's been approved and accepted by the IC in December. The call to action is please participate and contribute, and I hope that we be able to set up a greater harmonization between the advanced cooling solutions, the different sub-projects there, and the server group to make sure that we're working in harmony together for these more advanced cooling solutions, any type of liquid cooling solution that we're currently look at within the advanced cooling solutions group, which is door heat exchangers, cold plates, as well as immersion here. So with that, I want to say thank you for your time. And Archana, I'm not sure I left any time for questions, unfortunately.
You didn't, but I've been monitoring the chat, and I don't see any questions coming up from your session, and I don't see anything also in the Etherpad right now. However, like I was telling Pecan before, you just check back into this chat later, and if there are any questions, they might be posted here.
Okay.
Archana, if you don't mind, I pose a question
Sure.
to Jessica. Jessica, do you have a spec for component or material compatibility?
Good question. Good question. So there's actually within the immersion sub-project right now, there's another effort that was just initiated talking about material compatibility. And the idea there is to generate basically having matrices of available immersion liquids, since there are a lot of them on the market. It's not only one or two, right? But there's a lot of different immersion liquids on the market, and being able to provide really what materials that are compatible with that particular liquid. So there was just a panel here previously in the ACS work stream that